Okay, we're recording. So today we are going to basically continue where the last lesson left off, where we're dealing with maximums and minimums, but whether they be local or absolute. And you can probably already tell that the way we find them is what we call the first derivative test. And the first derivative test basically says that if f has a maximum or a minimum, and again, be it either local or absolute, at C, then C must be a critical number or critical value, same thing, number, value, and C comma F sub C is a critical point. But, as we learned last time, not all critical values are local maximums and local minimums. And again, a good reminder of that is to think about just good old-fashioned y equals x cubed. And if, let me go to this here. Actually, that's not the one I want. If we take a quick look at y equals x cubed, there we go. Oh, no, this one. There we go. There it is. If we take a look at y equals x cubed, right, clearly there's a flat spot on this graph where I would have a slope of 0. So if c in this case is 0, then f primed of c is going to be where the slope is 0. And that's not really a maximum or a minimum, right? Because it's, you know, it's increasing as I approach it, but then it's still increasing after I leave it. So that doesn't make it a maximum or a minimum. So how do we account for that? Well, how do we deal with this? Mathematically, we will say that we need a test that will tell us whether or not a function has a maximum or a minimum at a critical number. And we call that test the first derivative test. Now, the first derivative test isn't just finding the first derivative. It's about finding the first derivative and then testing its intervals. So we explore the intervals around the critical values. And that's the test. Note, please recall that the sign of a slope's value tells you if a function is increasing or, and of course that's positive, and then I meant to write or and I wrote of, or decreasing at that point. Okay, that's a lot of writing. I'll give you a sec to kind of catch up here. Here, I'll shrink it so it's all visible on one page. And I'll give you a sec to kind of catch up. While you're doing that, I'll run attendance here. There we go. Okay, so this is pretty similar to what I was doing the other day. I'm just kind of doing it a little more formally now. So here's what it says in your notes. If f is increasing to the left of a critical value, like for example, this critical value right here, if f is increasing, how would I know it's increasing? Well, I'd know because the slope would be a positive line on that side. Right? And if it's decreasing to the right, so this is going to be point A, if it's decreasing to the right, and that's a terrible tangent line because I just crossed. Okay, pretend that's a straight line, would you? So there we go, increasing slope, decreasing slope. Clearly, if you're increasing to the right of a point and decreasing to the, or sorry, let me say that again. If you're increasing to the left of a point and you're decreasing to the right of that point, you are clearly reaching a peak or a local maximum. But if you're at point B and you are decreasing slope-wise as you go to the left, so you have a negative slope to the left, and you have a positive slope to the right, then for sure you have a local minimum. And what you can do is, of course, make yourself an interval analysis. Just basically, you can even kind of set up a number line, right? Point A happens when you find your f primed of x, and you'll find that this A would of course be where f primed of x is 0, and this B will also happen where f primed of x is 0, and then you don't even really care how much the numbers are. You just care that on this side you'd be positive, and between them you'd be negative because the slope's always going down between them, and on this side you'd be positive again. And we usually do that like we did in the last lesson in a little chart. So let's do a couple of examples, and this will be kind of a short lesson today. It's a short class anyway, and then we'll call it a day after that. So let's find the local max and min values of x cubed minus 3x plus 1, and then they call this unit curve sketching. Let's actually make a sketch. Okay, so I could probably make you a very rough sketch just looking at this thing, right? What do I know about it? Well, I know that it's cubic, which means that it's an odd function, so one arm goes down, the other arm goes up. Its leading coefficient's a positive, so that means as x gets bigger forever, y gets bigger forever. So that means that it's definitely doing something like this, right? It's definitely going down to the left and up to the right. But I don't really know anything about where these numbers are. And you're going to find that in the grade 12 regular pre-calculus course, when you make sketches of these things, even based on the techniques you'll learn in grade 12 for how to find their x-intercepts, you still won't know how high the maximums and minimums are without the calculus that we're doing right now. So first derivative test, f primed of x is 3x squared minus 3, right? Derivative of 1 is nothing. So set that to 0 so I can find where these critical numbers are. And I get 3x squared minus 3. I'm going to divide both sides of the equation by 3, and I get x squared minus 1. Resist the temptation to move the 1 to the other side and go plus or minus the square root, because it's more useful to think about this in a factored form. Okay, it gives me the same numbers, right? It gives me that either x is 1 or x is negative 1, same two numbers. But this factored form is going to be useful because that's the easiest way to think about how you do your interval analysis. So the interval analysis, we've done this before, is basically a chart. So let's see. I have critical numbers, critical values at 1 and negative 1. So I want to know what's happening to the left of the leftmost critical value. So what happens when x is less than negative 1. I want to know what's happening when I'm between those critical numbers. And I want to know what happens when I'm past the rightmost critical number. So there's the 3 intervals of this function. Now, this function is made up of, I only care about whether it's positive or negative in these intervals. I don't really care for any specific numbers. So I'm just going to look at the factors. To tell if a number is positive or negative, all I got to do is look at its factors and tell, oh, did positives or negatives multiply to make this value? So let's take a look at the first factor. Will be x, what is it, x minus 1, or we'll do x plus 1 first. It doesn't matter what order, right? You can multiply in any order. and x minus 1. And then that's it. That's the two factors that matter. So then f, what's happening for the entire function. So in the interval when x is less than negative 1, take a number that's less than negative 1. How does negative 2 sound? So I'm thinking about the number negative 2. If this value here had a negative 2 in it for x, it would be negative. Again, I don't care that it's specifically negative 1. I just mean in general it's negative. If this number was negative 2, that would be negative. But when I multiply them together, a negative times a negative is positive. Therefore, we're increasing. Between negative 1 and 1, I guess the easiest number to work with will be 0. So if this number was a 0, I have a positive factor. If this number is 0, I have a negative factor. And a positive times a negative is decreasing. And notice people often ask, well, how did you know to pick 0? There's infinite numbers you could have picked between negative 1 and 1. Try any number you like. It won't change what these answers are. So I just picked the number that was easiest to think about in my head. How do you know that there wouldn't be a different answer if you picked a different number in this interval? Because I know how functions behave, and I know a cubic can only change directions twice. So that means there has to be 3 intervals when I do its derivative. See if you can get your head around how you know that. Anyway, let's pick a number bigger than 1. 2 sounds good. Positive, positive, and positive. So we're increasing again. So I'm ready to make a conclusion here, and I didn't leave myself very much room. So if you could squeeze it in there, great. Otherwise, I'm just going to write it over here. I can say that therefore, the point when x is negative 1, so approaching negative 1 from the left, what do you notice? You are increasing, then you are decreasing. Therefore, x equals negative 1 is a local maximum, right? It has to be. And you can say, you can figure out what that maximum is. You can just put negative 1 through here. So negative 1 cubed minus 1 times negative 1. So that's negative 1 plus 3 plus 1. So that local maximum is negative 1 comma 3. And the other conclusion we can make is that when x is approaching 1, we are decreasing as I come at it from the left, but then I'm increasing when I leave it heading right. So therefore, x equals 1 is a local minimum. Now, how do I know whether or not they're absolute maximums or minimums? Well, I go back to what I know about the basics of this graph. It goes up forever, it goes down forever. There's no boundaries on the domain of this function, so there can't be any absolute maximums or minimums. Okay? So x equals 1 is a local minimum, and let's see, run 1 through the formula if you want the point and you want to know how much that minimum is. 1 minus 3 plus 1 is negative 1. And now I can make a nice sketch of the diagram. All right? So I know that I have, again, at negative 1, I get to 3. At 1, I get to negative 1. And I know, again, that it goes down forever and up forever, or down forever on the left, up forever on the right. I can find the y-intercept to give me an extra point to put in. The y-intercept is 1. So there we go. I know I do something like this. And there we go. There's my sketch. Good enough. Sketches don't have to be terrifically accurate. If we want an accurate drawing, we'll go to Desmos. Any questions on how I did that? Okay, I don't see any questions in the chat, so hopefully everybody's following along. Okay, we gave a little more room for this example, so we don't have to go off screen here. But let's do a little more complicated looking equation. Let's do a quartic, x to the power 4. What do x to the power 4s look like? Well, they're even, so both arms go in the same direction. The leading coefficient here is a 1, a positive, so both arms are going up. So it is doing something like this. But I don't know how low these points go. Those are question marks. And I don't know how high that point goes. and that's what calculus is going to tell me. So here we go. First of all, we need to find a derivative. G primed of x is going to be 4x cubed minus 12x squared minus 16x, and the derivative of 1 again is nothing. Now in this case, again, I'm setting this to 0, which means I can divide both sides of the equation by 4. That's nice. But remember that when you're factoring, you always look for a greatest common factor first, and in this case I can still factor out an x. Do not divide both sides of the equation by x. Again, think factoring, because x as x equals 0 is one of my factors. If I divided both sides of the equation by x and I ignore the fact that x could be 0, well then I divided both sides of the equation by 0, and you're not allowed to do that. So factor first. Factor should be kind of your default setting. That should be the #1 tool in your toolbox when you're approaching algebra from now on. All right, speaking of factoring, there's a nice quadratic there I can factor. That's x minus 4, x plus 1, which means that I have critical points at, when x is 0, of course y is 0, because 0 times anything is 0. And what happens when x is 4? You can either run it through here or you can run it through there. I think I like the factored form better. It's a little easier than taking things to the power 4. So when x is 4, I'd have, oh, sorry, I guess I do have to go back to here, otherwise I just get 0. Actually, now that I look at it, 0, 0 is not the critical point. Sorry, I have to go back to the original equation. What was I thinking? When x is 0, I get -1. So that's one critical point. So that's for this, right? X can be 0, x can be 4, x can be -1. So when x is 0, I get -1. When x is 4, that'd be, oh boy, 16 times 16, 256 minus 256. Oh, that's nice. Those cancel. Minus 8 times 16. I'm going to need a calculator. I can't remember what 8 times 16 is. I guess it'd be 80 and 48. 128. So this is -128 minus 1. That's -129. Ah, there. I didn't need a calculator after all. And then, lastly, what happens when x is -1? When x is -1, I have 1 plus 4 is 5. 5 minus 8 is -3. -3 minus 1 is -4. There. There's my 3 critical points. Now, that's a little different than the sketch I had envisioned, right? I actually have something where it goes way down. So one of these downward minima is way lower than what I think the other one is. But again, I don't know for sure that these really are minima. It's possible that they're just places where the graph just kind of does this and it doesn't actually change direction there, right? It could be what we're going to call in our next lesson an inflection point. So I have to prove that those are critical points, I have to prove that those are maximums and minimums instead of just critical points. So I'm going to have to do an interval table. Now there's more intervals this time because there's more places where the slope is 0. So let's see. So what's the furthest left of our intervals? Well, our furthest left is -1. So what happens when x is less than -1? What happens when x is between the next two intervals, -1 and 0? What happens when x is between 0 and the next interval point, 4? And finally, what happens when x is more than 4? So I have 4 intervals to keep track of. The factors that I can use to calculate my interval signs are x minus 4, and x plus 1. And then let's figure out what f is doing. Okay, so what happens when x is less than -1? So that'd make this negative, and this negative. A negative times a negative times a negative is negative. We're decreasing. What happens when we're between -1 and 0? So I'm going to pick a number like, say, -0.5. That makes x negative. It makes x minus 4 negative. And it makes this positive. A negative times a negative times a positive is positive. So in this case, we're increasing. Between 0 and 4, 2 or 1. 1's a good number. We'll pick 1. That makes that positive, negative, positive, and multiplying those together makes negative. So we're decreasing again. And when x is greater than 4, everybody's positive. which means we're positive, which means we're increasing again. So what would it look like if neither of our examples have had a false positive yet? What if we'd have had one of these things really wasn't a critical value? It had just maybe changed direction without making a peak or a valley. Well, then you'd have the same direction twice in a row. And that didn't happen to us in the first example. It hasn't happened to us in this example. So I'm going to say therefore, and once again, I promised we'd finish this on the page, but we didn't. So hopefully you can write on the back or something. Therefore, I'm going to say that, let's see, as I approach -1, I am decreasing, then I'm increasing. So I am decreasing, then increasing. Therefore, the point, what was the y coordinate again for -1? -1, -4. So therefore, -1, -4 is a local minimum. And let's take the next point. The next point was 0, -1. Now what happens is you're approaching 0. You are increasing, and then you hit 0, and then suddenly you're decreasing. So 0, what was the point again? 0, -1 is a local max. And lastly, once again, when I get to the 4, I'm decreasing, going down, and then I'm going up. So the point 4, comma, -129. Now hold on a sec. -129. Now, are there any endpoints that could possibly be lower than this number? No. So I'm not going to say local max. I'm going to say an absolute max. Sorry, I meant to say minimum. Absolute minimum. Duh. How do I know it's absolute? Well, because again, I know both arms have to go up eventually. That's how x to the power 4 behaves. And there's no other place that this thing can change directions. So I'm ready to make a sketch now. So in my sketch, obviously I'm going to have to kind of play with scale a little bit here. But I'm going to have a point that goes 4 over and 129 down. So I'm going to go like 4 over this way, and then just, well, I'll be obviously counting in bigger steps there. And then 0 over and 1 down. So that's like going to be, if this is 129, that's going to be like way up there. And -1, -4 is going to be like there. So it's going to do something like this. It's going to go excuse me. And then it has to turn around there at that dot and come up. So it's going to look something like that. And just to see how well we did on our 2 examples, I did put them into Desmos here. So let me just get to Desmos. Okay, I can't find my cursor. There we go. There. And let's get to Desmos. And let's see. So, oh, that's yesterday's lesson. There we go. So here is our first example. And compare that to the sketch we made. Pretty good. We have our local max at -1,3, our local min at -1,1. And the next example, well, we're kind of off the screen, but remember, I can show you, I've shown you this before, but you can just play with that. We can make this, we know we have to go down to, say, -200. So let's go down to -200. There we go. And boom, and there it is. Our local minimum, our absolute minimum, and our local maximum. And there we have it. That's today's lesson. I'm going to stop the video.